In this lesson, we'll cover the last big idea of the unit. We're going to apply our idea of exponential functions to model situations. Okay, so just a quick refresher. When we studied exponential functions, we said that if b is greater than 1, we have an exponential growth function. If b is between 0 and 1, you have an exponential decay function. And that should make sense because if you multiply by a number which is greater than 1, you will, there are a lot of things you can write here, but I'm going to try to be a little more specific. You will increase in magnitude. Okay? You will increase in magnitude, meaning that the size, the sheer size of the number itself is going to grow. And if you multiply by a value between 0 and 1, you will decrease in magnitude. Okay, so the number is basically approaching 0. You can think of it as that way as well. Okay, let's build some models. So Lily is studying a virulent bacterial strain with an initial population of 8. If the population triples in number every day, what is the new population of bacteria after 2 weeks? So, hopefully you already know the answer to the question, but what I'm going to do is I'm going to use a table to help us out to begin with, okay? You don't need the table, but I'm just going to give you the table anyways. So we're talking about time in days and the population. So the initial population right from the beginning is 8. And it's said to be tripling every day. So after 1 day, I know you have 24, okay? But I'm not going to write 24. I'm going to write 8 times 3. I tripled the previous population. And then I know the answer. Okay? I know it's 24 times 3, but I'm not going to write down 24 times 3 or 72. I'm just going to write 8 times 3 squared. Okay, hopefully you can see why I'm doing this. So on the third day, after the third day, it's 8 times 3 cubed because I multiplied by 3 again. So there's an additional factor of 3. And let's do one more day. Why not? So hopefully you see a pattern. Okay, so the question is asking, what is the population after 2 weeks? Now, it would be very silly to fill this, continue on this table for 14 days. What I'm going to do is I'm going to build an equation which models the situation. So the population as a function of time in days is, hopefully you see that the exponent is exactly corresponding to the number of days. Okay, so let P of t represent population of bacteria. Let t represent time, and that's in days. Okay, so after 2 weeks, you're finding P of 14, right? Because 2 weeks is 14 days. Let's see. So wow, 38 million. $38,263,752. All right, let's keep going. So I have a Picasso painting. It's appreciating in value by 6% every 3 years. It is valued at $500,000 right now. How much will it be worth in 5 decades? You know what? You might not need a table, but I'm going to give you a table anyways. Okay, and later on we can do a generic strategy to build these models. So this is time in years. And we're talking about the value of the painting in dollars. So the beginning 500,000. Now, after 3 years, you can take that 500,000 and multiply by 1.06 because it's growing, it's appreciating by 6%. After another 3 years, you can multiply by 1.06 again. And then another 1.06 again. So now, this time, this example is a little harder because the exponent doesn't match up with the time in years. In fact, you can always get the exponent by taking the number of years and dividing by 3, which makes sense because you're gaining, you're appreciating by 6% every year. So it should be, oops, let's not do VP, let's do V. The value of the painting as a function of time, so it's 500,000 times 1.06, so it should be T over 3 because it's every 3 years, right? So let V of T represent the value of painting, and that's in dollars. Let T represent time, and that's in years. So 5 decades, that's 50 years. Whoa, 1.32 million. Not bad, not bad. So the lesson here is let's hold on to things that appreciate in value, okay? Because we're going to later look on at situations where the opposite is taking place. It's depreciating in value. You don't want to hold on to things that depreciate. And unfortunately, most of the things you own probably depreciate in value as opposed to appreciate. But that's just the way life works. All right, so let's do this example. I was gonna do a coronavirus example, but that's just, I feel like that was too depressing. So let's look at a town that has a population of 9,400 in 2005. 15 years later, its population grew to 26,500. You can easily replace these numbers with infected individuals, and you can talk about the time span. But yeah, we're just going to do this one. So it starts off at 9,400, grows to 26,500 in 15 years. Okay, so if you think about this, it should look something like this. So you have 26,500. You know what? Let's before I write this, I just want to show you something. So the population as a function of time is the original population times 1 plus the growth rate. And since this is, let's say we're trying to solve for the annual growth rate. So it's a growth rate per year. So I'm gonna, the exponent should be T because it's per year. So I know the population 15 years in the future is 26,500. I know the original population is 9,400. All right, so there you go. Let's solve for the growth rate. So 265 over 94. Let's take into the 15th root of both sides. And I'm going to subtract by 1 to get R. So let's approximate that. All right, so the town is growing at about 7.15% per year. Okay, So remember, we're averaging this out. So for example, some years the population might not grow as much, and some years it might grow more, but on average, we're going to say it's about 7.15%. So another interesting question you can do with these numbers or these models is like the price of homes. Okay, so I don't know. Let's say you bought a house for 500,000. Okay, and in 7 years, the house is valued at, I don't know. Let's say 1.2 million. That's actually not unreasonable. That might sound crazy, but this is not that unreasonable based on what's happening right now. So yeah, you can solve for the annual growth rate for the value of this house. You know what? Let's say 700,000. This is actually very, very realistic. I can see this happening in a lot of places in Toronto. Okay. There's actually a really interesting story recently about a gas station, and they sold it to because that piece of land, the people are going to use it to build a condominium, and it was astronomical. Like I think they bought the land they bought the gas station for 2 million, and they sold it for 60 something million, and that was just in 4 year span. Anyways, that's just an extreme example, but most of the houses right now, this is what happened. 7 years ago, it was not nearly the same price as it is today. And we're going to talk about the financial applications unit at the end of the course, and we're going to tackle this question again, because this is a very worrying situation on a lot of different levels, and we're going to explore those ideas hopefully. All right, so these were all examples of exponential growth. So let's do some examples of exponential decay. So Michelle bought a new car at 50,000. Unfortunately, it will lose 30% of its value each year. Now this is very extreme, okay? Most cars don't lose 30% of its value each year. And in fact, the way the depreciation of a car the way it works in reality is that the first 3 years you take a huge hit. The first 3 years, depending on the car you own, the type of car, some cars really don't retain its value very well, whereas some cars retain its value pretty well. So it depends on the car. But for most cars, the first 3 years, the hit is really hard. Okay. But anyways, we're just gonna make our life easy and say it's 30% each year. So what you can do is build a table. You know what? We'll do the table one more time. Okay. If you ever get stuck on a test, this is what I would recommend. So time in years. All right, so in the very beginning, you bought the car, $50,000. And in fact, the greatest moment of depreciation is when you pick up that new car, you sit inside, and that very first kilometer, that's like the most expensive kilometer you can possibly own the car. That like once you drive out of the parking lot of the dealership, it must have cost you a few $1,000s. That is gut-wrenching. Anyways, that's the way cars work. So a lot of people, that's why most of the cars nowadays, most transactions at the dealership are actually not for new cars. They're actually for used cars. So let's see. After 1 year, it's not the 50,000. And once again, I'm not interested in the number. I'm interested in how we find the number. So it loses 30%. So I guess that's a pessimistic way of seeing it. I guess the optimistic way of seeing it is that you retain 70%. okay, you retain 70%. Because if you lose 30%, you retain 70%. And guess what? After another year, you multiply by 0.7 again, and then another 0.7, and there you go. So let's build our model. So the value of the car as a function of time is 50,000 times 0.7 raised to the power of t. So let v of t represent value of car in dollars. Let t represent time in years. So how much is it worth after 8 years? Let's find v of 8. Oh, that is once again, like this is not realistic. You're not losing. This is a horrible deal. If it loses 30% of its value after every single year, yeah, it's not like that. So anyways, $2,882.40. And I would highly recommend you, before you buy a car, you should really look at how it depreciates. Like I said, some cars really retain their values very well. So this past year, for the 2 years running, the Wrangler retains the value the best. Yeah, I think it retains. I want to say 80%. You know, I can't remember, but you can Google the information. The Wrangler is the best in terms of retaining its value over its years. So that's why most people don't bother buying a used Wrangler. They just buy a new one, because you might as well get a new one since it retains its value so well. All right, so what do we have here? So a tungsten 187 is a radioactive isotope and has a half-life of 2 days. So if you've taken chemistry, you'll know that half-life means it spontaneously decays into half of its original amount after the half-life period, which in this case is 2 days. So let's say you have 100 milligrams. In 2 days, you have 50 milligrams. In 4 days, which is 2 half-life periods, you'll have 25 milligrams. If it was 6 days, you'll have 12.5 milligrams, because you have, and then you have again, and you have again. Anyways, they want to find out how much you have after 2 weeks. So I'll give you the general equation for half-life. So the amount, you can say the amount left is the original amount. Okay, now the base of the exponent is always half, because this is half-life. You're always losing half of what you have. And it's the time over h. H is the half-life period. All right, so if that's the case, we have 100 milligrams. 100 milligrams to begin with. You know, I'm going to do A of t. So the amount of tungsten 187 as a function of time in days. So the half-life is 2 days. You know what? Let's write the let statements. Why not? Let A of t represent amount of tungsten 187, and that's in milligrams. Let t represent time in days. All right, so 2 weeks, that's 14 days. Exact, 0.78125. Let's keep that exact. You can change that to fraction if you want. Oops. Oh, it's 25/32. Yep, whatever you prefer. So therefore, after 2 weeks, there will be 0.78125 milligrams. And I forgot to mention for the previous example, when you have your exponential decay functions, when you model it, usually it's your dependent variable, and then you have your original amount. Let's say this is, let's say original amount. I don't know what you're working with, whether it's money or value of a car, original population, whatever. Okay, and then it's 1 minus r. Okay, 1 minus r, and r is your decay rate. Okay, whereas in an exponential growth situation, it's the opposite, right? Instead of 1 minus r, it's 1 plus r, and r is now your growth rate. Okay, so hopefully you established that pattern without me writing that. And that makes sense, because if it's 1 minus r, then you end up with the b of the base between 0 and 1. If it's 1 plus r, you end up with the b greater than 1, which is what we said in the beginning. Exponential growth has a base greater than 1. Exponential decay has a base value between 0 and 1. All right. So, suppose you have a sample of carbon-14, which has a half-life of 3,186 years. And I think that's actually a lie, because I think the half-life of carbon-14 is more than that. I'm actually tempted to Google that, but you know what? Let's just say that's correct, because this is a very, very important number, because it helps you carbon date fossils, for example. You can tell how old a fossil is by determining how much carbon-14 is left. Anyways, how long will you have to wait until there's 10% of the original sample left? You know what? Let's use our half-life formula here. All right, so the half-life is 3,186 years. And if you want to wait until there's 10% of the original sample left, even though I don't know what the answer is exactly, it's a long time. It's a long, long time. Because just to reach 50% of the original sample, it's 3,186 years, right? To do 25%, you need 2 half-life periods. Oh my goodness, that's double of 3,186 years. So anyways, it's 10% left. I'm not going to do let statements this time, because I just want to save a bit of time, because the next thing I'm going to show you is pretty interesting, and that will require a lengthier explanation. So a of t, I'm going to let that be 0.1, because that's 10%, right? Like, think about it. If the original amount is 1, then how much you have left is 0.1. If you put this to be 100, then this would be 10. But anyways, when you do the math, it will end up being the same. So let's say you have 1 milligram and you have 10% left, which is 0.1. Oops, sorry, the exponent's t over 3186. But look, if you divide, right, you'll always get a ratio of 0.1. So it really doesn't matter what you state the original amount to be, you'll always end up with 0.1 here. Okay, so this is where we need a little lengthy explanation here. you have never done a calculation like this. Okay, you've never done a question where you are asked to use your algebra to solve for the exponent. So in grade 11, our expectation is really silly, to be honest with you. We want you to guess around. So you take your calculator and punch it in. So 0.5 to the power of, I don't know, let's say 9,000. Ooh, that's actually pretty good. So the answer is greater than 9,000 because you want it to be closer to 0.1. So I don't know, you change it to 9,500. Ooh, and then you keep playing around. Okay, so let's, ooh, 9,008. So I don't know, the answer is getting closer and closer. So you can play this game and guess around on the test, but anyone can do that. So you don't need me to teach you that. So I'll show you what you would have done if you learned some things from grade 12. So I'll first write this something very simple that we should all know. Okay, 2 cubed is equal to 8. We all know that, absolutely. So this is called exponential form. Okay, so you can actually rewrite the exact same idea but in logarithmic form. Now, why would you want to do that? Just give me a second. Let's write it in logarithmic form first. So you write logarithm. Remember, we're trying to express the exact same idea. So the base of the logarithm is the base of the power. Well, the base of the power is 2, so the base of the logarithm is 2. Now, the next number here I'm going to write is the argument of the logarithm. So I'm going to write 8. That's what the power is equal to once you evaluate it. Okay, and a logarithm, when you evaluate a logarithm, you're just asking yourself, what is the exponent? Okay, when you're asking what is the logarithm of logarithm base 2 of 8, you're basically asking yourself 2 to the power of what is equal to 8? 2 raised to the power of 3 is equal to 8. We just had it. So this is logarithmic form. So we're going to do one more, okay? We're going to do one more. Let's do 4 cubed is 64. We all know that's true. So let's do logarithmic form. Log base 4, right? Base of the power is 4, so the base of the logarithm is 4 as well. And the argument of the logarithm is 64, and the exponent is 3. So why would you want to rewrite it to logarithmic form? Because that will isolate your exponents. So logarithm, so the base of the power is half, so I write half. What is the power equal to? 0.1. T over 3186. So you know what? Multiply both sides by 3186. And there is your beautiful answer. Now, some calculators, you can actually evaluate this logarithm. Some calculators can change the base. So if you can't, okay, what you have to write, so my calculator can actually, so you're going to write logarithm of 0.1 divided by logarithm of half. So this one I won't explain because this is another relationship that you'll study in grade 12. But for now, just understand how to evaluate this using your calculator. So the answer was about 10,583.7 years. I'm really starting to wonder what's the half-life, but it's just that's just bothering me personally. Anyways, I'm really starting to wonder what's the half-life, but it's just that's just bothering me personally. Anyways, so after 10,583.7 years, you'll have 10% of your original sample left. So every time we ask you to solve for the exponent, you could guess around, but what you could also do is express it into logarithmic form, because that will isolate for your exponent and then you can just you can solve for your variable. Just be careful. If you have a calculator that can't change the base, then you just have to write logarithm of the argument over logarithm of the base. Okay, so if you have doubts, like here, log 64 to the, log base 4 of 64, you know what? There, log 64 over log 4. 3, right? You didn't need that, but I'm just showing you that it certainly does work.